The idea of congruence in geometry is one that's really important to us. We've already talked about what it means to be congruent segments or congruent angles. Congruent segments have the same length measurement. Congruent angles have the same angle measurement. Congruent polygons have all corresponding parts congruent. So all corresponding sides are congruent, all corresponding angles are congruent. And so when we look at this picture, it says, identify if there are any congruent figures in the picture. What are they and how do you know that they're congruent? Well, I think maybe what's easiest to work with first might be something like this rectangle right here. Okay? Look at, oops, hold on, I want to grab that. There we go. Okay, JIHG. That's a nice rectangle. Are there any other rectangles in this picture that are exactly the same as that rectangle? And the answer is yeah, it's right down here. QPRN, or QPNR. They're congruent. All their corresponding parts are congruent. They're exactly the same sides. We could look at that and we could show it in the coordinate plane pretty easily by finding the lengths of the sides. I mean, those sides are both 2, those are both 2, these are both 1, these are both 1. Corresponding sides are congruent. They're all right angles. Okay, they're congruent figures. But you recall that we also talked about the idea of a rigid transformation preserving everything about a shape. So if we do a rigid transformation, which would be a reflection, a rotation, or a translation of a figure, we should come up with a congruent figure, a figure that's identical to the original figure when we're done. And sure enough, this could be considered the result of a rigid transformation. There are a couple ways we could look at this rigid transformation. This could just be a translation down. Let's see now, if we take I to Q, we're going down 1, 2, 3, 4, 5, 6 units. So it could just be a translation where the x-coordinate does not change, but the y-coordinate goes down 6. So if the original, or if the two figures could be considered some sort of transformation, rigid transformation, they must be congruent. Are there other congruent figures? The rectangles are the easiest ones to look at here. Are there other congruent figures here? I think the next easiest one to look at might be, am I right, triangles here. And if I go over here, well, this is not a translation, is it? I didn't just slide this one over, did I? What did we do to make that work? Well, if I flip that left, right, and then, whoops, we flipped it. Oh, there we go. It's a flip of that, isn't it? It's like reflecting that in the y-axis. It's a reflection in the y-axis. K is 1 unit over, 1 unit over. And again, we notice all the corresponding parts are congruent. LK and TS are both 2 units long. PK and SU are both 2 units long. And ML and TU are the diagonal there. So we could use Pythagorean theorem, 2 squared plus 2 squared equals square root of 8. So each of these is a square root of 8 units long, which we could simplify if we need to. But really what we're after here is the idea of it's the result of a transformation. And same thing with our other triangles. Now, we have to be a little careful here. What happened from ABC to DEF? What kind of transformation is that one? Oh, that's a rotation of 90 degrees. And how do I know that? Well, I could very simply, if I rotate and only looked at ABC, what's that going to look like when it gets up there? Okay. Is that the same thing after rotate 90 degrees? A is up here at -1, 5, and B is left 2, down 1. Is that correct? Sure enough. Yes. D is in that position, E is in that corresponding position. So we can see that that's a result of a rotation. So yes, there are congruent figures in here, and we know they are congruent because we could describe them as a result of some sort of rigid transformation. Rigid transformation is a way to get congruent figures. Now, describe the congruence transformation or transformations that map one figure onto the other. Now, this is a little trickier than it looks. Because when I first look at this, I say, oh, it's a rotation. It's probably a rotation. And because if I look at my blue up here, A, B, C, D, A is at 1, 1, and it goes 2 right, and to get to D, it goes up 2 over 1. So let's just check the rotation and make sure that it's 180 rotation. Oh dear. When I rotate 180 degrees, H here is not in the correct position, is it? H is at 2, 1, not 1, 1. The parallelogram is not going the right way. Dear, 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 that makes things more difficult. All right. So what exactly is going on here? Is it a reflection? Is it actually what we're seeing here? I'll get rid of the suspense for you. Is we're seeing two different transformations here. We're seeing a combination of two transformations. And what's going on here is we're taking GH or EFGH, and we're going to slide the whole thing 1, 2, 3, 4, 5 units right. So I'm going to slide this 5 units right. So that's my first transformation. And then what am I doing? Then I'm reflecting in the x-axis. So there are two transformations. Or I could think of it the other way. I could say I took ABCD, reflected that in the x-axis, and then slid 5 units left to get EFGH. That's fine. Either way works. But we can use combinations to get there. So this is a result of so describe a congruence transformation. You might say to get from ABCD to EFGH, I guess we're going to go in that order. So I'd start by reflect ABCD in the x-axis, and translate 5 units left. We could have also actually switched the order. I could have translated it and reflected and gotten the same result as well. How about here? A transformation at JKL to MNP. Once again, it looks like I've got a rotation, but let's look at where LKJ is and MPN, and let's make sure it winds up in the same position. So if I rotate 180 degrees, oh dear, it's not working. But again, we get a relatively simple explanation for this. What are we going to do? Again, we're going to take JKL. We're going to translate it 1, 2, 3, 4, 5 units right. So translate JKL, triangle JKL, 5 units right. Then reflect an x-axis. So these compositions of rigid transformations give us a rigid transformation. We know that already, and we get congruent figures. What we're going to talk about are some very specific compositions now. And what we're going to see very quickly is that we could describe everything in terms of reflection. Translation and rotation could both be described in terms of reflection. A translation is simply a double reflection in parallel lines. It's a different way of looking at it, but it's one way of doing it. Now the line, you'll notice, is perpendicular. The line from A to A double primed contains A primed as well. That line is perpendicular to my lines of reflection, and we reflect once in the first line, K here. AB gets reflected in K, get A prime, B prime. We reflect it a second time, we get A double prime, B double primed, and we get, in essence, translation. And the amount of translation from A to A double primed is twice the distance between the lines, twice the distance between the mirrors of reflection. All right, now you're saying, well, that's great, but why do that? I mean, translation is so simple. Why would we complicate it by turning it into a double reflection? Honestly, it's just so that we could describe everything in terms of reflection. If I wanted to only have to deal with one type of transformation, the one I would choose is reflection. Then I wouldn't have to worry about translation or rotation or rules for them. I could do everything through reflection. And by the way, that's one of the reasons why all of them are rigid transformations, because they all could be expressed as a type of reflection, which is a rigid transformation. Now, the types of questions we're going to see with this are fairly straightforward. Notice the information that we're given here in our description. HB is 9. So from H to B is 9. That's this distance right here. And D to H double primed, D to H double primed is 4. Okay. What are they doing to us here? Let me highlight that with something a little bit different. There we go. That's the 4 right there. What are they doing to us here? It says name any segments congruent to any other segments. Well, we got a lot of congruent segments. Obviously, H prime, HG, H prime G primed, and H prime G double primed are automatically congruent. But what else do we have that's congruent? We know that since these are reflections, that DH primed and DH double primed have to be congruent. We know that HB and BH primed also have to be congruent because those are lines of reflection. Lines of reflection are always right smack in the middle of the 2 points that are being reflected. So these have to be congruent, and these have to be congruent. Same thing here. Those have to be congruent, and these have to be congruent. So once we know all that and recognize all this congruence is going on here, it says, does AC equal BD? So does AC, A to C, equal B to D? And that, yes, that has to be true because the lines are parallel. In order to be a double reflection, we have to have parallel lines, and we are indicated parallel lines. Okay, we've got our little triangles there. So yes, they are congruent because they are parallel lines. Yes, K is parallel to M. Okay. And then it says, what is the length of G prime? And again, that's fairly easy to figure out. To G primed, we're given HB and DH. H to H primed is 18. I'm sorry, H to H primed is 18. H primed to H double primed is 8. G to G primed, I feel like we're missing a piece of information here. I know G to G double primed has to be the same as H to H double primed. So this is 9, this is 9, this is 4, this is 4. That's 18, 22, 26. So G to G double primed is also 26. We don't know that G, well, yeah, we don't know necessarily that G to G primed is a midpoint. So I'm not sure that's 13. That's an interesting question that I thought I'd ask a different question. So, yeah, interesting. We'll get back to that one a little bit. Use the figures. The line between K and M is 1.6 centimeters. Well, if this is 1.6 centimeters, then from any point here to the corresponding point over here, from any corresponding points has to be how far? 3.2 centimeters. Okay? So that would be a single transformation of a translation 3.2 centimeters to the right. Same thing here. K and M is 1.6 inverse. What is the relationship between P primed and the line K? So P and P primed are my two. The relationship here is P primed is a reflection. It's supposed to be a C of P in K. And more of the same type of thing. So again, we get to see the idea that the distance is double, that there's a lot of congruence going on there. It's kind of neat, and there's a lot of stuff we can figure out, but again, it's a little puzzly. We can work with that. Rotation, I said, is also a double reflection. It's a double reflection at intersecting lines. So if I take AB, segment AB here, and I reflect it first in line K, as we're seeing, we get A prime, B prime. If I reflect it a second time in line M, I get A double prime, B double prime. And we can see pretty clearly that this is actually, in essence, rotating the object. In this case, the segment. Now, the interesting thing is that the measure of this angle of rotation, the measure of the angle of rotation is twice the measure of the angle between the lines. So that's really what it comes down to a lot for this particular problem. That's the big deal here that we deal with a lot in the homework, is that the angle of rotation is twice the angle between the lines. You won't be doing a lot of this stuff manually. You'll be doing this a lot with what's going on here. But it looks at this. Here I've got a fish apparently, and F is my original. F primed is my first reflection. F double primed is my second reflection. The angle between the two lines that we're reflecting is 70 degrees. What's the angle of rotation? It's 140-degree rotation. It's that simple. Same thing here. Again, we have an original, an image, and a second image. Its first reflection, second reflection are indicated by the arrows right here and here. So I know this is my original. So how can I describe this as a single transformation? Obviously, it's a rotation of 160 degrees, twice the measure of the angle between the lines. That's our big idea. It says a rotation of 76 degrees maps C to C primed. To map C to C primed using two reflections, what is the measure of the angle formed by the intersecting lines of the reflection? This is just working it backwards. It tells you the angle of rotation 76, so instead of being twice as much, if they want the angle between the lines of reflection, we have to do half of 76, and half of 76 is 38 degrees. Again, these are the types of questions you're going to see. Not super duper difficult, but it wants to get that idea across that the angle between the lines is half as much as the angle of rotation, or the angle of rotation is twice as much as the angle between the lines. All right, that's what we have on these types of rigid transformations, and we will see you in class.